Hello, dear listeners. Welcome to another Life History channel. There is a thing about the Earth. Every 100,000 years, with clockwork regularity, the planet freezes. Ice spreads from the poles. Glaciers move over the continents. Sea levels drop hundreds of feet. Entire ecosystems shift toward the equator. Then, with the same predictability, the ice retreats. The planet warms up. Life spreads back north and south. This has been happening over and over again for millions of years. The pattern is so regular that you could almost set your watch by it. Almost, because that is what makes this truly strange. The cycle isn't exactly perfect. It is close, incredibly close. But there are wobbles. There are variations. There are times when the ice should advance but doesn't. There are times when it should retreat but lingers, and no one knows exactly why. Before we dive into the story, I wanted to mention something personal. I recently had a medical procedure, but I am putting in extra effort to bring you these videos. I would love for you to be part of this journey by subscribing. Also, please share where you are right now and what time it is in the comments. I absolutely love reading them. Seeing someone in Tokyo at 3 a.m., Chicago at midnight, or London during a morning commute. It is fascinating how we are all present here at once. We know ice ages happen. We can measure them in ice cores drilled from Antarctica, in ocean sediments pulled from the deep sea floor, in rocks scraped and carved by ancient glaciers. The evidence is everywhere. We even know some of the causes. Earth's orbit changes shape. The planet wobbles on its axis. The tilt shifts slightly. These changes affect how much sunlight falls on different parts of the planet. They create cycles, predictable patterns in the amount of solar energy reaching the Earth. But here is the problem. These orbital changes alone aren't enough. The math doesn't quite work out. The wobbles in Earth's orbit should create temperature changes of maybe 1 or 2 degrees. Instead, we get ice ages, full glacial periods with ice sheets covering half of North America, climate changing so dramatically that entire species either go extinct, evolve, or migrate thousands of miles. Something is amplifying the signal, taking those tiny orbital nudges and turning them into massive climate swings. Scientists have been trying to solve this puzzle for more than a century. They have proposed dozens of theories, some elegant, some bizarre, some that looked perfect until new evidence proved them wrong. The answer, it turns out, involves everything. The oceans, the atmosphere, the ice itself, carbon dioxide locked in rocks and released by volcanoes, dust blown from deserts, plankton in the sea, forests spreading and retreating, all connected in ways we are still trying to figure out. And the truly unsettling part. We are living in one of the warm periods right now, between ice ages. The ice will come back, maybe in 10,000 years, maybe in 50,000 years. This cycle isn't over, unless of course we have broken it, which is a different question entirely. The first person to understand that ice ages actually happened wasn't a scientist. He was a Swiss carpenter and hunter named Jean-Pierre Perraudin. The year was 1815. Perraudin spent his days in the Alps, guiding travelers through mountain passes. He noticed something strange. Massive boulders were sitting in the middle of valleys, miles away from any cliffs they could have fallen from. The boulders didn't match the stone around them. They were granite, but the valleys were limestone. Perraudin had a theory. Glaciers had carried them. He told this to a Swiss engineer named Ignaz Wienetz. Wienetz laughed. Everyone laughed. Glaciers moved slowly, maybe a few feet a year. How could they carry house-sized blocks of rock over entire valleys? But Perraudin was persistent. He showed Wienetz the striations, long grooves carved into solid rock, all pointing in the same direction down from the mountains. Wienetz started paying attention. He looked at the rocks again. He measured the scratches. He talked to other mountain people. They all said the same thing. The glaciers used to be much bigger. You could see where they had been. The evidence was everywhere. Venetz was convinced. He presented his findings to the Swiss Society of Natural Sciences in 1821. Most scientists dismissed him. A few listened. One was a young geologist named Louis Agassiz. Agassiz was skeptical at first. He went to the Alps to prove Venetz wrong. He spent the summer of 1836 studying glaciers, measuring them, watching how they moved, looking at the rocks they carried. He came back convinced that Venetz was right, more than right. Glaciers hadn't just been bigger. They had covered most of Europe, all of Scandinavia, vast parts of Britain, and parts of Germany, France and Switzerland. Agassiz called it the Ice Age, Eiszeit in German. He presented his theory in 1837. The scientific community was unimpressed. The problem was catastrophe theory, the dominant theory of the time, the idea that Earth's features were shaped by sudden violent events. Most geologists believed in the biblical flood. They thought the boulders had been carried by rushing water. The scratches came from debris in the floodwaters. Everything could be explained by one great deluge. Agassiz was proposing something different. Slow change, gradual processes, ice advancing over thousands of years. It contradicted the prevailing view, but Agassiz had evidence. He showed his colleagues polished bedrock parallel scratches, U-shaped valleys carved by ice, and moraines long ridges of debris left behind when glaciers retreated. You couldn't explain all that with a flood. Slowly, scientists started to accept it. Charles Lyell, the most influential geologist of the era, was convinced in 1840. He saw the evidence in Scotland. Scratched rocks, erratics, glacial valleys, it all fit. By 1850, the Ice Age theory had become mainstream, but scientists thought there had been only one Ice Age, a period when glaciers covered the northern continents then melted away. The story ended there. The next discovery changed everything. In the 1860s, geologists started finding multiple layers of glacial deposits. In some places there were clear boundaries, old glacial debris, then a layer of soil and plant remains, then more glacial debris, then another soil layer, then more ice deposits. Each layer represented a different climate, glacial periods separated by warm periods. There hadn't been one ice age, there had been many. Scottish geologist James Geikie documented this in detail. He identified at least 4 separate glacial periods in Scotland, separated by warmer interglacial periods where plants grew and soils formed. The evidence kept mounting. In the Alps, geologists found the same pattern. Multiple glacial advances, each pushing rock and debris downhill, each retreat leaving behind different sediments. In North America, the evidence was even clearer. The Great Lakes region showed layer upon layer of glacial till, different ice sheets at different times, some reaching as far south as Missouri, others stopping in Wisconsin or Minnesota. But how could they prove it? How could they date rocks that were hundreds of thousands of years old? Radiocarbon dating wouldn't be invented until the 1940s, and it only worked on organic material younger than 50,000 years. The breakthrough came from an unexpected place, the ocean floor. In the 1950s, oceanographers started drilling into the deep sea, pulling up long cylinders of sediment from the bottom of the ocean. These cores contained the shells of tiny organisms called foraminifera, forams for short. Forams are single-celled creatures. They build shells out of calcium carbonate. When they die, the shells sink to the ocean floor, layer upon layer, year upon year, for millions of years. Here is what makes them useful. The shells contain oxygen, specifically oxygen isotopes, oxygen-16 and oxygen-18. The ratio between these two isotopes depends on temperature. When the Earth is cold and ice sheets are growing, more oxygen-16 gets locked up in the ice. That leaves more oxygen-18 in the ocean. Forams building shells during ice ages incorporate more oxygen-18. When the ice melts, the ratio shifts back. Scientists could measure these ratios. They could see the ice ages in the foram shells. Each layer of sediment represented a different period in time. You could read the climate history like a book. Sayre Emiliani did exactly that in 1955. He analyzed foram shells from Caribbean sediment cores. He found a clear pattern, warm periods and cold periods following each other over and over, going back hundreds of thousands of years. He established what he called oxygen isotope stages, odd numbers for warm periods, even numbers for cold periods. Stage 1 is our current warm period. Stage 2 was the last ice age. Stage 3 was a cooler period before that, and so on. The pattern was remarkable. Ice ages weren't random. They followed a rhythm, a cycle. Major glacial periods roughly every 100,000 years, with smaller variations in between. Other scientists confirmed it. They drilled cores from different oceans, the Atlantic, the Pacific, the Indian Ocean. Everywhere they looked, they found the same pattern, the same cycles, the same rhythm of the ice ages. Then came the ice cores. In the 1960s, scientists started drilling into the ice sheets of Greenland and Antarctica. These weren't like ocean cores. Ice cores contained actual ancient atmosphere, tiny bubbles of air trapped when snow fell and was compressed into ice. You could measure the carbon dioxide in those bubbles, the methane, the temperature when the snow fell. You could see volcanic eruptions as layers of ash. You could count annual layers like tree rings. The first deep ice core came from Camp Century in Greenland. Drilled between 1963 and 1966, it reached bedrock at 4,560 feet. It contained ice older than 100,000 years. The data confirmed what the ocean cores showed. Regular cycles of warming and cooling, ice ages following warm periods over and over. But the ice cores revealed something the ocean cores couldn't: the speed of change. Some of the transitions from ice age to warm period happened incredibly fast. Within decades, maybe even years, the climate could flip like a switch. In the 1990s, the Greenland Ice Core Project and the Greenland Ice Sheet Project 2 drilled even deeper cores. They found ice about 250,000 years old. Antarctic cores went back even further. The Vostok core, completed in 1998, reached ice 420,000 years old. Later cores from Dome C in Antarctica went back 800,000 years. 8 ice ages, 8 warm periods, all recorded in the ice. The pattern was undeniable. Scientists could now see the details. Every ice age wasn't uniform. There were cold periods and slightly less cold periods, advances and retreats. The climate wobbled even during glacial times. And the warm periods, the interglacials, weren't all the same either. Some were warmer than others, some lasted longer. Our current warm period, the Holocene, has been remarkably stable, unusually stable compared to previous interglacials. The evidence was overwhelming. Ice ages happened. They happened regularly. They followed a pattern, and we were living in a warm period between them. But knowing that ice ages happened wasn't the same as knowing why. The discovery of the pattern only deepened the mystery. What could cause such regular cycles? What force was powerful enough to freeze half the planet every 100,000 years? That question would take another set of discoveries to answer, and even then the answer would be incomplete, because the more scientists learned, the more complex the picture became. Ice ages weren't just about ice. They were about everything, the entire Earth system responding to a trigger. Some combination of triggers, all working together in ways scientists are still trying to unravel. Actually, that is kind of perfect. Learning about ice ages while trying to sleep. These massive slow changes happening over thousands of years. Nothing urgent, nothing that requires you to stay awake. Just the world doing what it always does, freezing, thawing, freezing again. Let the pattern carry you, the rhythm of it. 100,000 years, a long time to wait between ice ages. Right now, you have nothing but time. Here is the thing about orbits. They aren't perfect circles. The Earth doesn't glide around the sun like a ball on a string. It wobbles, it tilts, it shifts. And over thousands of years, those tiny changes add up to something huge. Ice ages. A Serbian scientist figured this out in the 1920s. His name was Milutun Milankovic. He was an engineer, a mathematician, a prisoner of war doing calculations in his head to keep his sanity. And he discovered something no one else saw. Earth's orbit changes, not randomly, but in patterns. Predictable cycles that repeat over and over. And when those cycles align just right, the planet freezes. 3 cycles, 3 different wobbles, each running on its own schedule. The first cycle is about the shape of Earth's orbit. Right now, our path around the sun is almost circular, almost but not quite. It is a little oval, stretched out. That shape changes over time, sometimes more circular, sometimes more stretched. The cycle takes about 100,000 years. When the orbit is more circular, Earth stays roughly the same distance from the sun all year. When it is more oval, we swing closer in summer and farther in winter. The difference isn't huge, but it matters. The second cycle is about the tilt of Earth's axis. Right now, our planet is tilted at 23.5 degrees, like a spinning top leaning at an angle. That tilt gives us seasons. When the northern hemisphere tilts toward the sun, it is summer there. When it tilts away, winter. But that angle changes. Over 41,000 years, Earth's tilt shifts between 22.1 and 24.5 degrees. More tilt means more extreme seasons, hotter summers, colder winters. Less tilt means milder seasons, cooler summers, warmer winters. And here is the key for ice ages. It isn't about how cold the winter gets. It is about how cool the summer stays. Ice builds up in winter. That is normal. But if the summer isn't hot enough to melt it all, the ice stays. Year after year, building up, thickening, spreading. Less tilt means cooler summers, which means more ice survives, which means glaciers grow. The third cycle is about the wobble of Earth's axis itself. Imagine a spinning top. As it slows down, it wobbles. Earth does the same thing. Our axis traces a slow circle in space. One full wobble takes 26,000 years. This wobble changes which season happens when Earth is closest to the sun. Right now, we are closest in January, Northern Hemisphere winter. In 13,000 years, we will be closest in July, Northern Hemisphere summer. This matters because it affects how extreme the seasons are. If you are closest to the sun during summer, that summer gets even hotter. If you are farthest during winter, that winter gets even colder. 3 cycles, 3 wobbles, each changing how much sunlight falls on different parts of the Earth at different times of year. Milankovic calculated all of this by hand, tables and charts and endless equations. He figured out exactly how much sunlight reached the Earth at different latitudes in different seasons for the past 600,000 years, and he found a pattern. Every 100,000 years, the cycles aligned. The orbit became more oval. The tilt decreased. The wobble put the northern hemisphere farthest from the sun during summer. All at once, less sunlight in summer, cooler temperatures, ice that didn't melt, glaciers that grew and grew and grew. He published his theory in 1920, then refined it in 1930, then wrote a full book called Canon of Insulation and the Ice Age Problem in 1941. No one paid attention. The scientific community ignored him. His math was too complex, his ideas too different. He was from Serbia, not a major research center, and World War II was happening. No one had time for theories about ancient ice. Milankovitch died in 1958. Still mostly unknown, his work gathering dust. Then in the 1970s, scientists started drilling ice. Long cylinders of ice pulled from Antarctica and Greenland. Ice that had been building up for hundreds of thousands of years, layer upon layer, each one a snapshot of Earth's ancient atmosphere. They could measure everything: temperature, carbon dioxide levels, dust in the air, pollen from plants, volcanic ash, all preserved in the ice like a frozen library. And they found the cycles. The ice showed clear patterns. Warm periods, cold periods, repeating over and over. And when they measured the timing, it matched Milankovitch's predictions almost perfectly. 100,000 years between major ice ages, 41,000-year cycles in the tilt, 26,000-year wobbles in the axis, all of it in the ice. Undeniable. They also drilled cores from the ocean floor, sediment that had been accumulating for millions of years. Each layer contained tiny shells from plankton. Those shells recorded the temperature of the water when the plankton lived. Warmer water, different chemistry in the shells. Colder water, different chemistry again. Same patterns, same cycles, same timing. Milankovitch was right. 30 years after his death, the evidence proved it. But here is the weird part. The orbital changes don't actually change the total amount of sunlight Earth receives. Not really. The planet gets the same energy from the sun whether the orbit is circular or oval, whether the tilt is steep or shallow. What changes is where that sunlight goes, and when. More sunlight at the equator, less at the poles. More in summer, less in winter. The total stays the same, but the distribution shifts. And that is enough. That tiny redistribution of sunlight is enough to trigger an ice age. Think about that. The difference in sunlight between an ice age and a warm period is only about 0.1%, 0.1%. That is all it takes. Earth's climate is balanced on a knife edge. A little push in one direction starts the ice growing. A little push in the other direction melts it back. The orbital cycles provide those little pushes. Regular, predictable, inevitable. But there is something strange about the 100,000-year cycle. It is the strongest pattern in the ice core data, the most distinct rhythm. But it shouldn't be. The orbital eccentricity, the stretching of Earth's orbit, has the weakest effect on sunlight, much weaker than the tilt cycle or the wobble cycle, yet it dominates the ice age pattern. Scientists call this the 100,000-year problem. Why does the weakest cycle create the strongest effect? No one knows for sure. There are theories. Maybe the other cycles amplify it somehow. Maybe feedback loops kick in. Maybe the ice sheets themselves create a momentum that takes 100,000 years to build and break. Ice is heavy, really heavy. A glacier a mile thick weighs trillions of tons. That weight pushes down on the Earth's crust. The land actually sinks under the ice. When the ice melts, the land slowly rises back up. But it takes thousands of years. Maybe that lag matters. Maybe the ice builds up slowly, gradually, over 90,000 years, getting thicker and heavier. Then something tips it over the edge. The ice collapses. Not all at once, but fast compared to how long it took to build. In 10,000 years it is gone. Then the cycle starts again. The Milankovitch cycles are still happening. Right now Earth is still wobbling, still tilting, still changing its orbit. The cycles never stop. Right now we are in a warm period, an interglacial. The ice sheets have retreated to Greenland and Antarctica. Sea levels are high. The climate is relatively stable. But according to the cycles, we should be slowly turning back toward the cold. Over the next few thousand years, the wobbles should realign. Summer sunlight in the high latitudes should decrease. Ice should start to build, but it is not. The Earth is warming fast, faster than any natural cycle would predict. That is us. Human activity. Carbon dioxide from burning fossil fuels is changing the atmosphere in ways that overpower the natural cycles. We have broken the pattern for now. Whether that is good or bad depends on your perspective. Living through ice ages is hard, but rapid warming creates its own problems. The Milankovitch cycles are still there, still working, still rocking Earth's orbit and Tilton axis. But we have added a new factor, a new force, and no one knows exactly how that will play out. Will we delay the next ice age, cancel it entirely, or just postpone it until carbon dioxide levels drop again thousands of years from now? The math Milankovitch did by hand in the 1920s still holds up. The cycles are real, the patterns are clear, but we have added a variable he never thought of: human civilization, industrial emissions, the ability to change our own planet's climate. The wobbles continue. Silent, slow, inevitable. The Earth keeps tilting and spinning and circling the sun. The same cycles that have driven ice ages for millions of years. But now we are part of the equation too. And the next chapter of Earth's climate story is being written by both natural cycles and human choices. Ice remembers everything. Every wobble, every tilt, every shift in Earth's orbit, trapped in those frozen layers, waiting to tell its story to anyone who drills deep enough to listen. So how do wobbles in space actually create ice on Earth? It seems impossible. Earth tilts a little more, the orbit stretches slightly, and suddenly glaciers appear, miles thick, covering entire continents. The connection isn't obvious, but it is real, and it all comes down to one thing: summer, not winter. That is the strange part. You would think ice ages start because winters get colder, more snow falls, temperatures drop, ice builds up. But it doesn't work that way. Ice ages start because summers get cooler, just a little cooler, not enough to notice on a daily basis, but enough so that last winter's snow doesn't completely melt. Think about it. In Canada, in Alaska, in northern Europe, it snows every winter, feet of it. But every summer most of it melts. The cycle resets. Winter adds snow, summer takes it away. Balance. But what if summer can't finish the job? What if the temperature stays cool enough for some snow to survive? Not all of it, just patches in the valleys, on north-facing slopes, places where the sun doesn't hit so hard. That leftover snow sits there through the next winter. More snow falls on top of it. The old snow gets compressed, turns into ice, gets heavy, gets dense. The next summer comes, still a little cooler than normal. More snow survives. More ice builds up, year by year, decade by decade, century by century. The ice grows, at first just snowfields, then patches of ice, then glaciers, small ones in the mountains. But they keep growing, spreading, flowing downhill like frozen rivers. And here is where it gets interesting. Ice changes everything around it. White surfaces reflect sunlight. Fresh snow reflects about 80% of the sun's energy back into space. Dark surfaces absorb it. Forests absorb about 90% of sunlight. Ocean water absorbs about 95%. So when ice covers the land, less heat gets absorbed. The area stays cooler, which means more ice survives the next summer, which means more sunlight gets reflected, which means even cooler temperatures. It is a feedback loop. Ice creates conditions that make more ice. Scientists call this the albedo feedback. Albedo just means reflectivity. High albedo means more reflection. Low albedo means more absorption. A landscape covered in forest has low albedo, dark green trees absorbing sunlight, warm ground, snow melts quickly in spring. The same landscape covered in ice has high albedo, Bright white surface bouncing sunlight away, cool ground, snow barely melts. The Milankovitch cycles don't create much cooling on their own. The change in sunlight is small, less than 1%, but they trigger the feedback loop, and the feedback loop does the heavy lifting. It starts in the far north, northern Canada, Scandinavia, Siberia. These places are already cold. They already get snow every winter. They are right on the edge, barely melting all their snow every summer. When the orbital cycles reduce summer sunlight by even a tiny amount, these places tip over. Snow starts to accumulate. Ice starts to grow. The ice spreads outward, south from the Arctic, across Canada, across northern Europe into Russia. Glaciers thousands of feet thick, moving, grinding, reshaping the land. And as the ice spreads, it reflects more sunlight, which cools more area, which allows more ice to form further south. The feedback loop accelerates. But there is another feedback loop happening at the same time. The ocean. Cold water holds more dissolved gas than warm water. You can see this with soda. Cold soda is fizzier. Warm soda goes flat. Same principle with ocean water and carbon dioxide. As the Earth cools, the ocean absorbs more CO2 from the atmosphere. Less CO2 in the air means less greenhouse effect. Less greenhouse effect means cooler temperatures, which means the ocean absorbs even more CO2. Another feedback loop, this time involving the chemistry of the entire planet. Scientists can measure this in ice cores, tiny bubbles of ancient air trapped in Antarctic ice. Each bubble is a sample of Earth's atmosphere from thousands of years ago. During ice ages, CO2 levels drop to about 180 parts per million. During warm periods, they rise to about 280 parts per million. The pattern is clear. Less CO2 equals colder climate. More CO2 equals warmer climate. The Milankovitch cycles start the process, but the feedback loops amplify it. They turn a small change in sunlight into a massive climate shift. Still, it takes time, a lot of time. Ice doesn't appear overnight. It builds gradually over thousands of years, every summer leaving a little extra snow, every winter adding another layer. The ice sheet grows inch by inch, year by year. Imagine living at the start of an ice age. You wouldn't notice. Not in your lifetime. Maybe summers feel a bit cooler. Maybe snow lingers a bit longer in the mountains. But nothing dramatic. Nothing obvious. Your grandchildren might notice more. The snow line creeping lower. Glaciers in the mountains growing. Winters lasting longer. 1,000 years later, the changes are undeniable. Glaciers have advanced miles. Forests have retreated. The climate has shifted. 5,000 years later, ice covers half the continent. Everything has changed. The ice grows fastest at the beginning, when it is small and just in the mountains. Then it slows down as it gets bigger. Spreading over flat land takes longer. The ice has to flow, push outward under its own weight. At its peak, the ice sheets are 2 miles thick in places. The weight is incredible, so heavy it pushes down Earth's crust. The land actually sinks hundreds of feet under the ice. All that ice has to come from somewhere. The ocean. Water evaporates from the sea, falls as snow on the ice sheets, gets locked up in glaciers, doesn't flow back. Sea levels drop. During the last ice age, the ocean was 400 feet lower than today. Coastlines were completely different. Land bridges appeared. England was connected to Europe. Alaska was connected to Russia. You could walk between them. The ice keeps growing until something stops it, until the feedback loops reverse. And here is the thing. The same orbital cycles that trigger the ice age eventually end it. Earth keeps wobbling. The tilt changes. The orbit shifts. After tens of thousands of years, the cycles swing the other way. Summer sunlight increases just a little bit, but enough, the ice starts to melt at the edges. slowly at first just the southern margins, but melting creates its own feedback loop. As ice melts, it exposes the dark ground underneath. Dark ground absorbs more sunlight, which creates more warming, which melts more ice. The albedo feedback works in reverse. The ocean warms up slightly. It releases some of that dissolved CO2, more greenhouse gas in the atmosphere, more warming, more melting. Ice that took 90,000 years to form can collapse in 10,000 years, sometimes faster. The end of an ice age happens much quicker than the beginning. But here is what is weird. The orbital forcing, the push from the Milankovitch cycles, is just as strong going into an ice age as coming out. The change in sunlight is symmetrical, equal but opposite. So why does ice grow slowly but melt fast? No one knows for sure. Maybe feedback loops. Maybe they are stronger in one direction. Maybe it is easier to melt ice than to build it. Maybe there is a threshold effect, a tipping point where everything speeds up. Or maybe it is about where the ice is. Ice at high latitudes near the poles is stable, cold all year, hard to melt. But as ice spreads south, it reaches warmer, more vulnerable areas. When the climate shifts, the southern ice melts fast, and once it starts, the feedback loops take over. The whole system isn't linear. Small changes can have huge effects. Thresholds matter. Timing matters. How different cycles interact matters. That is why the 100,000-year cycle dominates. Even though the 100,000-year cycle has the weakest direct effect. It isn't just about sunlight. It is about how the system responds, how feedback loops amplify the signal, how ice and ocean and atmosphere all interact. Earth's climate isn't a simple machine. It isn't like turning a dial. It is more like a pinball game. You hit the ball and it bounces around, hitting different bumpers, changing direction, building momentum. Small differences in the initial hit make huge differences in where the ball ends up. The Milankovitch cycles are the initial hit. The feedback loops are the bumpers. And ice ages are the result of the ball bouncing around the system for 100,000 years. We can see this in the data. Ice cores show it clearly. Climate doesn't change smoothly. It jumps, sudden shifts, rapid transitions, then long periods of stability. Ice builds gradually, slowly, steadily, for 90,000 years. Then suddenly, in a few thousand years, it is gone. The climate flips, temperatures spike, sea levels rise, the world transforms, and then it stays warm for 10,000 or 15,000 years, an interglacial period like the one we are in now. Stable, comfortable, easy to forget that ice ages are the normal state because they are. Over the past million years, Earth was in an ice age about 90% of the time. Warm periods are brief interruptions, pleasant breaks between long frozen eras. We are living in one of those breaks, the Holocene. The current interglacial. It started 11,700 years ago when the last ice age ended. And according to the orbital cycles, it should be ending soon. Geologically speaking, the wobbles should be aligning to start the next ice age. Summer sunlight at high latitudes should be decreasing. Snow should be starting to accumulate. Ice should be building. But it is not because we have added something new to the system, something the Milankovitch cycles never accounted for. Us, human civilization, industrial emissions, carbon dioxide from burning coal, oil and gas. We have raised atmospheric CO2 from 280 parts per million to over 420 in just 200 years. That is faster than any natural cycle, faster than the ocean can absorb, faster than plants can use. We have swamped the system and broken the pattern. The orbital cycles are still there, still working. But we have added so much greenhouse gas that the cooling effect doesn't matter. The Earth is warming instead. Fast. We have essentially cancelled the next ice age, at least for now, at least for the next few thousand years, maybe longer. Whether that is good or bad depends on your perspective. Ice ages are hard. Glaciers destroy everything in their path. Sea levels drop. Climate zones shift. Entire ecosystems collapse and rebuild. But rapid warming has its own problems. Different problems. Rising seas, changing weather patterns, species that can't adapt fast enough. The wobbles continue regardless. Silent, slow, patient. The earth keeps tilting and spinning. The cycles keep turning. The same forces that have driven climate for millions of years. But now there is a new force in the equation. Us. And no one knows exactly how that will play out. How long will our impact last? What happens when CO2 levels drop again, thousands of years from now? Ice remembers every wobble, every tilt, every shift recorded in frozen layers. A library of climate history extending back 800,000 years, maybe more. And it is still recording, still building, still waiting to tell its story to anyone listening. So there is a problem with all the theory. A big problem, one that scientists noticed pretty quickly when they started looking at the actual data from ice cores and ocean sediments. The cycles don't match. Remember, Milankovitch proposed 3 cycles. The tilt cycle at 41,000 years, the wobble cycle at 23,000 years, and the orbit shape cycle at 100,000 years. But here is the thing. The orbit shape cycle is by far the weakest. It changes the amount of sunlight reaching Earth by only about 0.1%, almost nothing. The tilt cycle is much stronger, changing sunlight by about 15%. The wobble cycle is in the middle, changing it by maybe 5%. So strictly logically, you would expect the tilt cycle to dominate. The 41,000-year rhythm should be the strongest signal in Earth's climate record, and for a while, it was. Go back far enough in the ice core data before about 1 million years ago, and you see exactly what you expect. A strong 41,000-year pattern. Ice ages come and go every 41,000 years. The tilt cycle is in charge. But then something changes. Around 1 million years ago, maybe a little earlier, the pattern shifts. The 41,000-year cycle fades into the background, and the 100,000-year cycle takes over, becomes dominant, controls the rhythm of the ice ages. This makes no sense. The weakest forcing somehow produces the strongest response. It is like tapping a wine glass with your finger and getting a massive ringing sound, but hitting it hard with a spoon and getting just a quiet clink. The system reacts backward. Scientists call this the 100,000-year problem, or sometimes the Milankovitch problem, because it suggests something is wrong, or at least missing, in the theory. The data is clear, undeniable. For the past million years, ice ages have followed a nearly exact 100,000-year cycle. You can see it in ice cores from Antarctica, in ocean sediments from all over the world, in cave formations, in ancient beaches. 8 ice ages in the last 800,000 years, each lasting about 90,000 years, separated by 10,000 to 15,000 year warm periods. The pattern is too regular to be random, too consistent to be a coincidence. Something is pacing it, something with a 100,000-year rhythm. But the only natural cycle at that frequency, the orbital eccentricity cycle, is too weak. The math doesn't work. The forcing is small. The response is huge. It is like pushing a kid on a swing. A small push at the right time can create a big swing. Resonance. Timing matters more than power, but even resonance has limits. You can't push the swing with your pinky finger and expect it to go over the bar. There has to be enough force to work with. The eccentricity cycle changes almost nothing. Earth's orbit goes from slightly elliptical to slightly less elliptical. The difference in sunlight is negligible, less than the difference between a cloudy day and a clear day. Yet somehow this tiny change triggers massive ice sheets miles thick covering continents lasting tens of thousands of years. Something else must be happening. An amplification mechanism. A way for the system to take a weak signal and turn it into a strong response. Scientists have been arguing about this for decades, proposing theories, testing models, trying to solve the puzzle. One idea involves the ice sheets themselves. Maybe they have their own internal rhythm, their own natural cycle that matches the orbital cycle. Think of it like this. Ice sheets grow until they get too big, too unstable, then they collapse. Not because of external forcing, but because of their own weight, their own dynamics. Maybe it takes about 100,000 years for an ice sheet to grow to the point where it becomes unstable, where the bottom starts melting from pressure and friction, where the whole thing starts to slide and break apart. The orbital cycles might just provide a nudge, a gentle push that sends an already unstable system over the edge. The timing looks like it is controlled by the orbit, but really it is controlled by the ice. This theory has some support. Scientists know ice sheets can collapse quickly, much faster than they grow. The end of the last ice age happened in just a few thousand years. Sudden, dramatic, like flipping a switch. But the theory has problems too. Why would the ice sheet cycle be exactly 100,000 years? That is a very specific number. And why would it synchronize so perfectly with the orbital cycle? Coincidence seems unlikely. Another idea focuses on carbon dioxide. We know CO2 levels dropped from about 280 parts per million to about 180 during ice ages. That is a big change. And CO2 is a powerful greenhouse gas. Maybe the carbon cycle has its own rhythm. Maybe the ocean absorbs and releases CO2 on a 100,000-year cycle. And maybe that cycle is linked to orbital changes somehow. But that just moves the problem. Why would the carbon cycle operate on a 100,000-year timescale? What drives it? The weak orbital forcing still has to do too much heavy lifting. Some scientists think multiple cycles interact. The 100,000-year cycle doesn't work alone. It combines with the 41,000-year cycle and the 23,000-year cycle. They beat against each other, creating interference patterns, reinforcing certain frequencies like musical notes. Play two notes close together and you hear beats, a throbbing rhythm. The combined sound is different from the notes alone. Maybe Earth's climate is responding to the combined signal of all three orbital cycles, and maybe the way they combine creates a strong 100,000-year beat, even though the individual 100,000-year cycle is weak. The math for this gets complicated. You have to model how different frequencies interact, how the climate system responds to multiple inputs at once, how feedback loops amplify some signals and dampen others. Computer models can do this, and some models produce a strong 100,000-year signal from weak orbital forcing, but the models require careful tuning, specific assumptions about how ice sheets behave, how the ocean circulates, how carbon dioxide moves between atmosphere and ocean. Change the assumptions slightly, and the 100,000-year signal disappears, or becomes too strong, or shifts to a different frequency. This bothers some scientists. If the theory only works with very specific assumptions, maybe it isn't the right theory. Maybe we are missing something fundamental. There is another strange thing about the 100,000-year cycle. It isn't perfectly regular. Sometimes it is 80,000 years. Sometimes 120,000. It averages 100,000. But there is variation. If the orbital cycle directly controlled ice ages, you would expect perfect regularity. The orbital cycle is like clockwork, precise, predictable. It doesn't vary. But ice ages do. Sometimes they skip beats or double up. The rhythm has hiccups. This suggests the climate system has some independence, some internal variability. It isn't just passively reacting to orbital forcing. It is doing its own thing, and the orbital cycles influence it. Give it a tempo, but don't completely control it. Imagine a drummer keeping time. Most of the time they hit the beat exactly, but sometimes they are a little early, sometimes a little late. They add fills, change the rhythm. The underlying tempo is still there, but there is creativity, variation. Maybe Earth's climate is like that. Orbital cycles provide the tempo, but the climate system improvises around it. Or maybe the climate system is chaotic in the mathematical sense, sensitive to small differences. Tiny changes in starting conditions make huge differences in outcomes. Chaotic systems can look random, but are actually deterministic. They follow rules, but the rules are so sensitive that prediction becomes impossible, like weather. We can predict a few days ahead, but not weeks or months. The system is too chaotic. Maybe ice ages are chaotic too. Orbital cycles provide some structure, some predictability, but chaos adds noise. The variation makes every ice age a little different. That would explain why the pattern isn't perfect, why ice ages sometimes come early or late, why the 100,000-year rhythm has wobbles. But it makes solving the problem harder, because chaos means we can't predict exactly. We can't say for sure what causes what. We can only talk about probabilities, tendencies, rough patterns. Some scientists think we are asking the wrong question. Maybe there isn't one cause, one mechanism, one explanation. Maybe ice ages result from multiple factors all working together, sometimes reinforcing each other, sometimes cancelling out. The system is too complex for simple answers. Orbital cycles matter, feedback loops matter, ice sheet dynamics matter, the carbon cycle matters, ocean circulation matters, even random chance matters. All these things interact, creating a complex system, and the 100,000-year pattern emerges from that complexity, not because of one dominant cause, but because of how everything comes together. This is unsatisfying in a way. Scientists like clean explanations, simple theories, elegant solutions. Complexity feels messy, hard to test, hard to prove. But maybe that is how the Earth works. Maybe climate is inherently complex. Multiple causes, multiple feedbacks, no single answer. Ice cores keep providing data. More detail, better resolution. Scientists can now see changes happening over decades, sometimes years. The records are incredibly precise, and the more precise the data gets, the more complex the picture becomes. There are cycles within cycles, sudden jumps, gradual trends, regional differences, global patterns. Every answer raises new questions. Every solution reveals new problems. Why did the 100,000-year cycle start 1 million years ago? What changed? Before that, the 41,000-year cycle dominated. What flipped the switch? Some scientists think the ice sheets got bigger. Before 1 million years ago, ice ages were smaller. The ice didn't spread as far south, didn't get as thick, didn't last as long. Maybe once ice sheets reached a certain size, they started behaving differently, became more stable, harder to melt, taking longer to build and collapse, and that shifted the system's natural frequency from 41,000 years to 100,000 years. But why did the ice sheets get bigger? What allowed them to grow larger than before? Maybe Earth cooled slightly, a long-term cooling trend over millions of years. As Earth cooled, ice could survive further south, build thicker, last longer. Or maybe ocean circulation changed, the way currents move heat around the planet. A small change in circulation could allow ice to accumulate differently. Or maybe mountain ranges rose higher. The Himalayas, the Rockies. Higher mountains mean more area above the snow line, more places for ice to start growing. All these things likely played a role, slowly, gradually, over millions of years until the system crossed a threshold, and the rhythm shifted. The 100,000-year problem isn't solved, not because scientists aren't smart enough or don't have enough data, but because the system is genuinely complex. Multiple causes, multiple effects, no single explanation captures it all, and maybe that is okay. Maybe some questions don't have simple answers. Maybe the universe is messy, complex, full of interactions we are still trying to figure out. Ice remembers it all. Every cycle, every wobble, every shift locked in frozen layers waiting to tell its story. We can read that story now, extract the data, plot the graphs, see the patterns, but understanding why the patterns exist, that is harder. That takes time, more research, more thinking. The 100,000-year problem isn't solved, but we are getting closer. Every study adds a piece. Every model refines our understanding. Every ice core reveals new details. And in the meantime, the cycles continue. Silent, patient, indifferent to our confusion. The Earth keeps wobbling, tilting, moving through space. The ice keeps recording, building, waiting. So what really drives ice ages? We have the orbital cycles, the wobble, the tilt, the stretch. We know they matter. The timing fits too well to be a coincidence. But we also know they aren't enough. The forcing is too weak, especially that 100,000-year cycle. It changes almost nothing, yet somehow it runs the whole show. Something is amplifying that weak signal, turning a whisper into a roar. But what? The answer might be the ice itself. Ice sheets don't just sit there. They aren't passive. They don't just grow when it is cold and melt when it is hot. They have their own behavior, their own dynamics, their own way of changing the world around them. Think about what happens when an ice sheet forms. Snow falls in northern Canada, Scandinavia, Greenland. Year by year the snow piles up, compacts, turns to ice. At first it is just thick, a layer of ice covering the ground, maybe a few 100 feet deep. That isn't enough to change much, but it keeps growing. The ice gets thicker, heavier, starts to flow under its own weight, spreads outward, moves south, and here is where things get interesting. Ice is white, bright white. It reflects sunlight. About 80% of the sun's energy bounces back into space. Dark ground absorbs sunlight. About 80% gets absorbed, turned into heat, but ice reflects it, sends it away. The ground stays cold. This creates a feedback loop. More ice means more reflection. More reflection means less heat. Less heat means more ice can survive, which means more reflection. The cycle feeds itself. Scientists call this the ice albedo feedback. Albedo means reflectivity. Ice has high albedo, dark soil has low albedo. The difference is huge. Once an ice sheet reaches a certain size, it starts creating its own climate, making its own weather. The bright surface reflects heat. The cold air over the ice sinks, flows outward, pushes away warm air. The ice sheet becomes self-sustaining. It doesn't need orbital cycles anymore. It makes its own cold. But there is more. Ice sheets change the land underneath them. Their weight is enormous. A mile of ice weighs about 900 tons per square foot. That is like parking 600 cars on every square foot of ground. The Earth's crust can't support that weight. Over thousands of years it bends, it sinks. The land under the ice sheet drops, sometimes hundreds of feet. This matters because of how ice sheets grow. They need elevation, cold temperatures, snow that doesn't melt in summer. When the land sinks, the ice surface sinks too. Lower elevation means warmer temperatures, even a few degrees warmer. This makes the ice more vulnerable, more likely to melt. So ice sheets create their own problems. They grow, get heavy, push the land down, lower their own elevation and make themselves easier to melt. This might explain the timing, why ice ages last so long, why they end relatively quickly. The ice sheet grows for tens of thousands of years. getting thicker, spreading further. The land underneath slowly sinks. The whole system becomes more and more unstable. Then something tips it over. Maybe the orbital cycles provide a nudge, a little more summer sun, a little warmer temperatures, just enough. The ice starts to melt, not everywhere, just at the edges, just a little. But that small amount matters because ice sheets have another property. They insulate the ground beneath them. The bottom of an ice sheet isn't at air temperature, it is warmer, sometimes close to freezing, sometimes actually melting. Pressure helps. A mile of ice creates massive pressure. Pressure lowers the melting point. Ice can melt at temperatures below 32 Fahrenheit, so the base of the ice sheet is wet, slippery, and when the ice sheet starts losing mass at the edges, the whole thing can start to slide, to move faster, to break apart. That is how ice sheets collapse. Not by melting in place, that would take forever. By sliding into the ocean, breaking into icebergs, floating away. The collapse can be fast, geologically speaking. A few thousand years, maybe less. Ice that took 90,000 years to form is gone in 10,000. And once it starts collapsing, the feedbacks reverse. Less ice means less reflection, more dark ground exposed, more sunlight absorbed, more heat, more melting. The loop feeds itself again, but in the other direction. This explains a lot why ice ages last so long, why they end fast, why the system seems to have two stable states, glacial and interglacial, cold and warm, with rapid transitions between them, but it still doesn't fully explain the 100,000-year rhythm. Why does it take about 100,000 years for ice sheets to reach that tipping point? Why not 50,000? Why not 200,000? The answer might involve multiple factors. Ice sheet dynamics, orbital cycles, carbon dioxide, ocean circulation all working together. Carbon dioxide drops during ice ages. We know this from ice cores. Bubbles trapped in ancient ice show it clearly. About 280 parts per million during warm periods. About 180 during ice ages. That is a big drop. And CO2 is a greenhouse gas. Less CO2 means less heat trapped. Cooler temperatures, more ice. But why does CO2 drop? What causes it? The ocean. The ocean holds about 50 times more carbon than the atmosphere. It is a giant reservoir. Carbon constantly moves between ocean and air, dissolving in, bubbling out. The balance changes. Cold water holds more CO2 than warm water. Like a cold soda, it stays fizzy. Warm it up and the gas escapes. During ice ages, the ocean cools, especially in polar regions. Cold water sinks, taking dissolved CO2 with it down into the deep ocean where it stays locked away for thousands of years. Less CO2 in the atmosphere means cooler temperatures, which means more ice, which means more reflection, which means even cooler temperatures. Another feedback loop. But there is more. Ocean circulation matters. The way currents move heat around the planet. The conveyor belt of water flowing from equator to poles and back. During ice ages, this circulation changes, slows down, maybe even stops in some areas. Fresh water from melting ice dilutes the salt in the ocean, changes its density, disrupts the flow. When circulation slows, heat doesn't move as efficiently. The poles get colder, the tropics might get warmer. The whole climate system reorganizes. These circulation changes can trigger rapid shifts, sudden cooling, sudden warming. Climate doesn't change smoothly. It jumps, flips from one state to another. Scientists see this in the ice core records. Temperature doesn't rise gradually. Sometimes it spikes 10 degrees in just a few decades, then stays stable for centuries, then jumps again. These rapid changes suggest the climate system has thresholds, tipping points. Push it far enough and it flips to a different state like a light switch, not a dimmer. Ice sheets might have their own tipping points. Grow them to a certain size and they become stable, hard to melt. Shrink them below a threshold and they collapse quickly. The orbital cycles might push the system slowly toward these thresholds over thousands of years. Then one summer is just warm enough. One winter adds not enough snow. The ice sheet crosses the threshold, starts to collapse. The timing looks controlled by orbits, and in a way it is. But the orbits just provide the tempo, the push. The system's own dynamics do the rest. It is called internally amplified forced oscillation. The external force is weak, but the system reacts strongly because of its own properties, its own feedbacks, its own instabilities. Like pushing someone on a swing. You don't have to push hard, just at the right time. The swing does most of the work. It has its own momentum, its own rhythm. You just keep it going. Earth's climate might work the same way. Orbital cycles are the push small, regular, predictable. But the climate system has its own natural rhythm, a tendency to oscillate between glacial and interglacial states. The orbital cycles keep that oscillation going, provide the timing, but the amplitude comes from the system itself. Feedbacks, ice, carbon, ocean, all amplifying the signal. This explains why the 100,000-year cycle dominates even though the forcing is weak. The system is tuned to respond at that frequency, like a radio tuned to a specific station. It picks up that signal and amplifies it. But why is the system tuned to 100,000 years? Why not some other frequency? It is still unclear. It might have to do with how long it takes for ice sheets to grow to critical size, how long it takes for the land to sink enough, how long it takes for carbon to move between atmosphere and ocean. All these processes have timescales. None are instant. They take thousands of years, maybe tens of thousands, and when you combine them all, the natural timescale of the system comes out to be about 100,000 years. Or maybe it is simpler. Maybe the 100,000-year orbital cycle, while weak, is persistent enough, pushing at the same frequency, never stopping, never changing to pace the system. And over time, the system synchronizes with it, like a metronome. Tick, tick, tick. Keep it up long enough and everything starts moving to that beat. Ice cores show this synchronization. The timing is too regular to be random. 8 ice ages in the last 800,000 years, each lasting about 90,000 years, each ending in about 10,000. The pattern repeats, but not perfectly. There is variation. Some ice ages last 80,000 years, some 120,000. Interglacials vary too. Some longer, some shorter. The current one is already 11,700 years old. Longer than average. This variation suggests the system isn't completely controlled by orbital cycles. There is some independence, some chaos, some randomness. Carbon dioxide. It sounds so simple, just a gas in the air, but it is one of the most important players in this entire story. When we talk about cycles of ice and heat, about the Earth freezing and thawing, carbon dioxide is always there in the background. Silent, invisible, but powerful. Let's try to see how it actually works. Not just the big picture, but the details. How do we know that carbon dioxide acts as an amplifier for ice ages? What is the real proof, and why does it matter so much? First, think about what we actually see in the records. Ice cores from Antarctica and Greenland are like time machines. Scientists drill down more than 2 miles into the ice. Each layer is a pressed sheet of 1 or 2 years of snowfall. As the snow fell, it trapped tiny air bubbles. Those bubbles are still there. Ancient air, frozen for hundreds of thousands of years. When scientists pull up an ice core, they can measure the air from, say, 20,000 years ago. They look for carbon dioxide in those bubbles, and there is a clear pattern that emerges. Every time the planet was cold, an ice age, the carbon dioxide in the air was low, about 180 parts per million. Every time the planet warmed up, CO2 rose back to about 280 parts per million. This isn't just a coincidence. The rises and falls match the timing of the ice ages almost exactly. The coldest times always have the lowest CO2. The warmest times have the highest. The lines on the graph move together like two dancers locked in step. Now here is where it gets interesting. CO2 changes don't just follow the temperature. Sometimes CO2 starts to change before the major warming begins. Sometimes it lags a bit behind, but the two are always connected. When CO2 goes up, the planet warms. When it goes down, the planet cools. It is a partnership. How do we know CO2 actually causes the change and isn't just tagging along? That is a fair question. People used to argue about this, but the evidence is now strong. Think about how greenhouse gases work. Carbon dioxide isn't the only one, but for these timescales, it is the most important. Sunlight hits the Earth. The surface absorbs the energy. Much of it radiates back as heat. As infrared light, greenhouse gases like CO2 trap some of that heat. They let sunlight in but slow the heat escape, like a thin blanket. If there is more CO2 in the air, more heat stays in. If there is less, the planet loses heat faster. This isn't a theory, it is basic physics. We can measure it in the lab. We can see it on other planets too. Venus is hot, not just because it is closer to the sun, but because its atmosphere is thick with carbon dioxide. So when ice cores show CO2 dropping during ice ages, it means Earth's blanket is getting thinner. More heat escapes, the planet cools, and ice sheets can grow. When CO2 rises, the blanket gets thicker, Earth holds on to more warmth, and the ice sheets melt. But how important is CO2 really? Is it just a little helper or a big amplifier? Here is what the numbers say. During an ice age, the difference in CO2 is about 100 parts per million, 180 in an ice age, 2080 in a warm period. That 100 ppm change is enough to shift global temperatures by about 4 to 6 degrees Celsius. That is 7 to 11 degrees Fahrenheit. A huge swing, enough to turn Canada into a frozen wasteland or a green forest. Enough to cover New York City in a mile of ice or fill it with trees and rivers. The fact that CO2 changes align so closely with temperature is a big clue, but there is more. Scientists can compare the timing in detail. When the planet starts to warm at the end of an ice age, the first thing that happens is a small increase in sunlight at high northern latitudes. That is the orbital cycles at work. Not much energy, but just enough to start melting the edge of the ice. Then, a little later, CO2 starts to rise. It isn't instant. It takes a few hundred years. But as CO2 rises, the warming accelerates. The ice melts faster. The planet shifts from cold to hot in just a few thousand years. It is like starting a fire. The orbital cycles are the spark, but CO2 is the fuel. Once the fire gets going, it burns hot and fast. Without that fuel, the spark wouldn't be enough. Scientists have tried to model this with computers. They take the orbital changes alone and ask the model what happens. The answer is clear. You get a little warming, but not enough to explain the actual record. Add in the CO2 changes, and the model matches the ice core data almost perfectly. The temperature swings make sense. The timing works. The evidence comes together. There is another way to see the power of CO2. Look at the numbers. The direct effect of changing CO2 from 180 to 280 ppm is about 2 degrees Celsius of warming, just from the greenhouse effect. But that is only half the story. When the planet warms, other feedbacks kick in. Ice melts. That changes the reflection of sunlight. As we saw before, more dark land means more heat absorbed. The oceans warm up and release even more CO2. The atmosphere holds more water vapor, which is another greenhouse gas. All these feedbacks add up. The total warming is about double what you would expect from CO2 alone. So CO2 acts as both a driver and an amplifier. It starts the process and then helps push it even further. The system feeds itself. A little warming releases CO2, which causes more warming, which releases more CO2. The cycle continues until something stops it. But where does all this CO2 come from, and where does it go? This is where the ocean comes in. The ocean is the true giant in this story. It holds about 50 times more carbon than the air. Most of it is dissolved, like sugar in tea. Some is in the deep ocean, some near the surface. The balance between these places is always changing, but slowly, during ice ages, the oceans are colder. Cold water can hold more CO2, just like a cold soda stays fizzy longer. So when the planet cools, the oceans absorb more carbon from the air. The CO2 level in the atmosphere drops. This helps cool the planet even more. But when the planet starts to warm, the oceans warm too. Warm water can't hold as much CO2. The gas bubbles out, escaping into the air. The CO2 level rises, making the planet even warmer. That is another feedback loop. There are other ways carbon moves between air and sea. Tiny plankton in the ocean use CO2 to build their bodies. When they die, some of their remains sink to the bottom, taking carbon with them. Ocean currents mix deep and surface waters, bringing old carbon up or sending new carbon down. Even winds over the ocean can change how much CO2 bubbles out. During ice ages, ocean currents and winds are different. The whole system slows down. Less mixing means more CO2 stays trapped in the deep ocean. When the ice age ends, the system speeds up. The deep ocean releases its carbon. The air fills with CO2 again. Scientists have looked for evidence of these changes. They studied ocean sediments, layers of mud at the bottom of the sea. These layers hold tiny shells from plankton, and each shell has a record of the water's chemistry. By measuring the carbon in the shells, scientists can see when the deep ocean was storing more CO2 and when it was releasing it. The results match the ice core data. During the coldest parts of ice ages, the shells show the deep ocean was full of CO2. The atmosphere was low in CO2. When the planet warmed, the deep ocean released its carbon and the air filled up again. There are clues from the land too. During ice ages, massive dust storms swept over the continents. Glaciers ground up rock, creating huge clouds of fine dust. Some of that dust blew over the oceans, especially the Southern Ocean near Antarctica. This dust carried iron, a key nutrient for plankton. When the dust fell into the sea, plankton bloomed. They pulled extra CO2 from the air, helping to lower atmospheric carbon even further. When the ice age ended, the dust storms faded. Less iron, fewer blooms, less CO2 drawn from the air. So carbon dioxide is being pulled in many directions at once. Ocean, land, winds, plankton, every part matters. But the overall pattern is clear. Cold times mean low CO2, warm times mean high CO2, and the swings are big enough to change the entire climate. Some people wonder if the changes in CO2 are just a side effect. Maybe warming causes carbon to rise, not the other way around. But experiments and models say otherwise. Fix CO2 at ice age levels and the planet stays cold even if sunlight increases. Add CO2 and the planet warms fast even if sunlight doesn't change much. The effect is real and powerful. You can see it even in the speed of the transitions. At the end of every ice age, the warming is fast, just a few thousand years. This matches the speed at which CO2 rises in the ice cores. When CO2 jumps, the planet follows. Ice melts, forests return, animals and people spread into new lands. If CO2 didn't matter, the change would be slower. The small increase in sunlight from orbital cycles isn't enough to explain the rapid jump. But with the rise of CO2, the planet has a booster, a turbo button. That is why the change can be so sudden. So the evidence for CO2 being an amplifier is strong. Ice cores show the timing. Ocean sediments show the storage and release. Models show the effect on temperature. The details fit, but there are still open questions. For example, exactly why does CO2 drop so much during ice ages? Why does the system switch between storing carbon and releasing it in the ocean? What causes the deep ocean to lock away so much CO2 for tens of thousands of years and then suddenly let it go? Some scientists think it is about how the ocean circulates. During ice ages, winds and currents change. Deep water becomes more isolated from the surface. Less mixing means more carbon trapped. When the planet warms, ice melts, winds shift, mixing increases. The deep ocean exhales its carbon. Others point to plankton. Maybe giant dust storms during ice ages supercharge the plankton, allowing them to pull more CO2 from the air. When the dust faded, plankton slowed down, and CO2 rose back up. There is even a role for the land. During ice ages, forests shrink, deserts grow, soil carbon changes. All these move carbon from one place to another. But the biggest player is still the ocean. Scientists are still working out the details. They are building better models, looking for new clues, drilling deeper ice cores, collecting more ocean mud. But the big picture is clear. CO2 is the master amplifier. It doesn't start the ice ages, but it makes them much more dramatic. It turns small changes in sunlight into massive climate shifts. It is the reason the planet can swing from Sahara-like deserts to frozen tundra and back again, and the numbers are big. During an ice age, about 10 million square miles of land are covered in ice. When CO2 rises, most of that ice melts. Sea levels rise by more than 400 feet. Coastlines move. Rivers change course. Ecosystems shift overnight. At least in geological terms, we see the impact everywhere. In plant and animal fossils, in layers of pollen in lake beds, in ancient soils buried under old ice. The story is always the same. When CO2 is low, life retreats. When CO2 rises, life fills back in. This is why scientists pay so much attention to CO2. It might be invisible, but it isn't silent. It leaves its mark all over the planet. And once you start looking, you see it everywhere. Here is something else to think about. The amount of CO2 in the air during these cycles is tiny compared to all the carbon in the ocean and rocks. But even small changes in the air make a huge difference. The planet is sensitive. The climate system balances on a knife edge. It doesn't take much to tip it one way or the other. A slow drift in CO2, a small change in sunlight, a shift in ocean currents, the feedbacks do the rest. And that is why ice ages are so regular, but also unpredictable. The orbital cycles set the timing, but CO2 sets the volume. The music plays, but the loudness changes. Sometimes a whisper, sometimes a roar. We can even see the CO2 amplifier working today. Since the Industrial Revolution, humans have added about 130 parts per million of CO2 to the air. That is more than the difference between an ice age and a warm period. The result is a planet warming faster than at any time in the last 10,000 years. But that is another story. Right now, we are talking about natural cycles. The way the planet has moved between ice and heat for millions of years. The CO2 amplifier has always been there. Sometimes quiet, sometimes loud, but always in the background. It is a reminder that the planet isn't just shaped by rocks or ice or sunlight. It is shaped by invisible things too. Tiny molecules in the air, bubbles trapped in ice, gases dissolved in the sea. all connected, all playing a part. When you look at the big picture, you see a system that is both fragile and powerful. It can flip from one state to another given the right nudge, but it always finds a new balance, a new rhythm. CO2 is part of that rhythm. Not the only part, but one of the most important, the amplifier that turns small changes into big ones. The reason the planet can change so much and so fast. And the proof is all around us, in the ice, in the ocean, in the land, in the stories told by ancient air and old mud and fossil forests. So next time you hear about carbon dioxide, remember it isn't just a number or a gas or something in the news. It is one of the main reasons the Earth has frozen and thawed over and over again for millions of years. But CO2 isn't the only amplifier. The oceans themselves play a huge role too. Their currents, their hidden heat, their deep secrets, and when they change, everything changes. The ocean is a world of its own. It isn't just a big pool of water, it is layered in motion, and always shifting in ways that are hard to see from the surface. If you could slice the ocean open, you would see something like a giant sandwich, warm water on top, colder water underneath, and the deepest layers far below that. Each layer holds different amounts of heat and carbon, and how these layers mix and move changes everything for the planet. Let's start with what is actually happening down there. The ocean isn't still. Currents flow through the surface, sometimes for thousands of miles. The Gulf Stream, for example, brings warm water from the Gulf of Mexico all the way across the Atlantic to Europe. That is why winters in London aren't as cold as winters in Quebec, even though both places are about the same distance from the North Pole. Ocean currents carry heat. They act like conveyor belts, moving warmth from one part of the globe to another. But the real action is deeper down. Think about the ocean's great conveyor belt. Scientists call this thermohaline circulation. That just means it is driven by heat and salt. Here is how it works. In the far north near Greenland, surface water gets very cold. Sometimes it even freezes to form sea ice. When that happens, salt is left behind in the water. This makes the water heavier and saltier, so it sinks. This cold, salty water then flows south along the bottom of the Atlantic, sliding under the warmer water above. At the same time, something similar happens in the Southern Ocean near Antarctica. Cold, salty water sinks and spreads north along the ocean floor. It can take hundreds or even thousands of years for a single drop of water to complete this loop around the world. This slow, deep movement is how the ocean stores and releases heat. It also locks away carbon. When surface water sinks, it takes carbon with it, trapping it in the deep. When deep water comes back up, it can release that carbon again. So what is the proof that this circulation matters for ice ages? Scientists have looked for clues in the mud at the bottom of the ocean. Every year, tiny shells, dust particles, and other debris settle on the sea floor. Over time, these layers build up like pages in a diary. By drilling into the mud, scientists can pull up long cores, samples that give a record going back hundreds of thousands of years. Inside these cores are clues about the past. Some are chemical, like the amount of carbon in shells from tiny plankton. Others are physical, like the size and shape of their shells, which can tell you about the temperature of the water when they lived. One of the best-known examples comes from the Atlantic Ocean. During the last ice age, the deep Atlantic was different from today. It was colder, and the water was more isolated from the surface. Scientists can tell this because chemical fingerprints in the shells show a buildup of carbon in the deep sea. Less carbon was getting out to the surface and into the air. Why would this happen? During ice ages, winds and currents shift. The ocean lid tightens, less mixing between surface and deep water. The conveyor belt slows down. Cold, salty water is still sinking, but it isn't pulling as much surface water down with it. The deep ocean becomes a carbon trap. Then, when the planet starts to warm, the system wakes up. Currents strengthen. There is more mixing between deep and surface. The carbon locked below starts to leak out, rising up and escaping into the air. This is one reason CO2 rises as an ice age ends. It isn't just land or air changing. It is the ocean releasing its stored carbon. Let's look at a real example. In the Southern Ocean around Antarctica, there is a special place where deep ocean water rises to the surface. It is called upwelling, like a fountain in slow motion, bringing cold, carbon-rich water from the bottom. Today, this upwelling brings nutrients that feed massive plankton blooms. But during ice ages, things were different. Evidence from seafloor cores suggests there was less upwelling during the coldest times. Wind patterns changed, and the water didn't rise as much. This meant less carbon moving from deep water to the surface, and less escaping into the air. The result was lower CO2 in the atmosphere, helping to keep the planet cold. But as the ice started to retreat, the winds shifted again. Upwelling increased, bringing more deep water and its trapped carbon to the surface. More CO2 bubbled out and filled the air. The planet warmed even faster. This isn't just a guess. Scientists can see the timing in the mud. Types of plankton change. The chemistry in the shells shifts. The layers show a pulse of carbon coming out of the deep ocean right as the planet warms. The match is almost perfect. Now, let's talk about how heat moves in the ocean. The ocean holds much more heat than the air. In fact, the top 10 feet of the ocean hold as much heat as the entire atmosphere above it. When the ocean takes in extra heat, it doesn't just warm up instantly. It absorbs the energy, mixes it around, and releases it slowly over time. During ice ages, much of the ocean's heat is locked away from the surface. Covered by thick ice in the far north and south, the deeper parts stay cold and dark. But as ice melts, the sun can warm a larger area. The surface warms up, and more of that warmth can mix down into the depths. This mixing isn't even. It depends on wind, storms, and how salty the water is. Sometimes a shift in wind patterns can push warm water deeper, spreading heat through the ocean. Other times, the ocean can trap cold water under a layer of warm water, keeping the surface mild while the depths stay frigid. A good example comes from the North Atlantic. Today, when the Gulf Stream slows down, Europe can get cooler winters. If the whole conveyor belt system changes, it can shift the climate much more. During ice ages, evidence shows the conveyor belt was weaker. This trapped more cold water in the deep ocean and helped ice sheets grow. Scientists have even found clues of sudden events, moments when ocean currents changed fast. In some ice cores and seafloor records, you can see signs of sudden warming or cooling that happened in just a few decades. These climate jumps might have been caused by major changes in ocean circulation. For instance, a sudden rush of fresh water from melting ice could shut down the conveyor belt. This would stop heat from moving north, keeping the north cold while leaving heat to build up in the tropics. Let's be specific. About 12,800 years ago, the world was warming up after the last ice age, but suddenly, the North Atlantic cooled sharply for about 1,000 years. This period is called the Younger Dryas. What happened? Evidence points to a massive flood of fresh water pouring into the North Atlantic from melting ice sheets. This fresh water stopped the formation of cold, salty water that normally sinks and drives the conveyor. With the engine stopped, heat couldn't move north as easily. The result was that Europe and parts of North America became much colder, almost like the Ice Age had returned. Then, just as suddenly, the system restarted. The conveyor belt sped up again. Warm water flowed north, and the planet finished thawing out. The whole world shifted into the warmer climate we have had since. The ocean isn't just a background player. It is the memory of the climate system. It stores heat for centuries, even millennia. It absorbs carbon and holds it, releasing it again only when currents shift. The evidence for all this comes from many places. Ice cores, seafloor mud, the chemistry of tiny shells, and even ancient shorelines that show where sea levels used to be. There is more. During ice ages, sea level drops by over 400 feet because so much water is locked in ice sheets. This exposes huge areas of the sea floor, changing the shape of continents. Shallow seas disappear. The edges of the ocean move far out from where they are now. This affects how heat moves around the planet too. New coastlines change wind patterns, ocean currents, and how solar energy is absorbed. When ice melts and sea levels rise, shallow seas flood back, new currents form. The whole system gets a fresh start. Evidence shows these changes in ocean shape and depth played a role in the onset and end of ice ages. Let's not forget the role of life in the ocean. Tiny plankton float near the surface, using sunlight to grow. They take carbon out of the water. When they die, some sink to the deep ocean, carrying carbon with them. This is sometimes called the biological pump. During ice ages, there are signs that this pump worked harder. More plankton grew, more sank, and more carbon got locked in the depths. How do we know? Scientists look at fossil species and the chemistry in their shells. They can tell when plankton blooms were larger. These blooms are often helped by dust blowing off the land, carrying nutrients like iron into the sea. We talked about this before, but here is something new. The strength of the biological pump is tied tightly to ocean circulation. When the deep ocean is more isolated, the pump works harder because nutrients stay near the surface longer. But when currents start moving again, deep water rises and brings nutrients from below. The pump slows down and more carbon escapes back into the air. It is a delicate balance. Ocean life and ocean circulation are linked. All of this matters because the ocean sets the pace of climate change. The air can warm or cool in just a few years, but the ocean takes centuries to fully respond. That is why the end of an ice age isn't just a smooth, steady thaw. It is a stop-start process. Warm years, then sudden freezes, then back to warming. The clues are everywhere if you know where to look. In the North Pacific, scientists found layers of mud showing sudden spikes in plankton growth that match times when ocean currents changed. In the Indian Ocean, cores show shifts in salt and temperature that align with major changes in ice sheets. Even in the deepest parts of the Atlantic, there are chemical traces showing when deep water was full of carbon and when it let it go. The big picture is this. The ocean isn't just a passive tank of water. It is an active player in Earth's climate. Its currents move heat and carbon around the globe, and when those currents change, the whole climate can shift, sometimes very fast. So we have talked about the role of the ocean and how it moves heat and carbon around. But even with all that, there is a question hanging in the air. Why is the timing of ice ages so regular? Why does Earth freeze and thaw almost like clockwork every 100,000 years? It isn't random. Something sets the tempo. Here is where things get a little weird, and honestly kind of fascinating. Scientists have been trying to solve this puzzle for decades. They looked at every clue they could find. They drilled ice cores from Antarctica, pulled mud from the bottom of the sea, counted layers in cave rocks. All these clues point to the same thing. Ice ages come and go with a steady beat, about every 100,000 years. But here is the catch. The changes in Earth's orbit, the so-called Milankovitch cycles, don't line up perfectly with this 100,000-year rhythm. Earth's orbit does get more or less stretched over time, sometimes more like a circle, sometimes more like an oval. This change, called eccentricity, happens in cycles of about 100,000 years. So you might think, okay, that explains it. But when you look closer, it doesn't quite add up. The effect of this orbital stretching on sunlight is actually pretty weak. It changes the amount of sunlight Earth receives by only a tiny amount, not nearly enough to freeze the planet or melt ice sheets on its own. For a long time, scientists thought there had to be something else, something that takes these small regular nudges from Earth's orbit and turns them into huge swings between ice and warmth. Enter a strange idea called stochastic resonance. The name sounds complicated, but the idea is simple when you break it down. It is about noise, and by noise, scientists don't just mean sound. They mean any random, unpredictable change in the system. A little chaos, a little background static. Let's use an example. Imagine you are trying to push a child on a swing, but instead of standing behind them, you are standing to the side. You are giving small, regular pushes, but they aren't perfectly aligned with the motion of the swing. The swing barely moves. Now imagine there is a gusty wind, sometimes strong, sometimes weak. Most of the time, the wind just makes things a little shaky, but every once in a while, the wind and your push align just right. Suddenly, the swing flies much higher. That is stochastic resonance. The small regular push alone isn't enough. The random gusts alone aren't enough. But together, they can be huge. The system resonates. It gathers energy from both the regular push and the random noise, and suddenly you get a big swing. Now imagine Earth's climate as that swing. The regular pushes are from Earth's orbit, very slight changes in sunlight happening on a steady schedule. The noise comes from many places, volcanic eruptions, changes in ocean currents, maybe even things like dust storms or shifts in how plants grow. Each one is random, sometimes big, sometimes small, sometimes nothing. Most of the time, these random changes just jiggle the climate a little. A colder year here, a warmer year there. But every once in a while, the random noise aligns with the regular push from the orbit. And that is when something big can happen. The system flips. Ice sheets grow or they melt. The climate swings from cold to warm or back again. This idea helps explain why the timing of ice ages is so regular, even though the changes in sunlight are so small. It isn't just about the size of the push. It is about the timing and the way the system responds to both regular and random forces. Let's be a bit more concrete. Scientists ran computer models where they tried to build an ice age. They put in the small changes from Earth's orbit. Then they added some noise, random changes in temperature or how much snow fell from year to year. When they did this, something surprising happened. The climate in the model started jumping from warm to cold and back on a regular schedule. Even though the pushes were small and the noise was random, together they created a steady rhythm. Every 100,000 years the system flipped. This is the heart of stochastic resonance. The climate system is sensitive not just to big things, but to small random changes too. When you combine a weak regular force with a little chaos, you can get a much bigger effect than you expect. Another way to think about it. Imagine trying to roll a heavy ball over a small hill. If you push gently, nothing happens. The ball just rolls back. If you give a huge push, you can get over the top. But what if the hill is bumpy and the ground is shaking a little all the time, just enough to get the ball close to the edge? Most of the time these shakes do nothing. But if you time your push with one of those shakes, you only need a small force to get the ball over the top. The movement of the ball isn't just about your push. It is about the push and the bumps working together. For Earth, the bumps are those random changes, volcanoes, ocean shifts, even sudden changes in sea ice or dust. The push is the slow, steady sunlight change from the orbit, and when the two align, the climate tips over. This idea can be hard to picture, but it shows up in other places too. Sometimes small regular signals get hidden by noise, but if the noise is just right, it can actually help the signal stand out. Stochastic resonance is about that. A little chaos can actually make a pattern stronger, not weaker. And here is the wild thing. Scientists have tested this idea in the lab, not with a whole planet of course, but with simple systems. They use electrical circuits or even water tanks. They add a small regular signal, like a very gentle pulse. Then they add random noise. When they tune the noise just right, the system starts to jump in time with the pulse. It is like magic. Too little noise, and nothing happens. Too much noise, and it is just chaos. But with just the right amount, the pattern emerges. So what does this mean for ice ages? It means the planet's climate might act like one of these systems. The changes in Earth's orbit are the regular pulse. The random stuff, volcanoes, ocean shifts, dust storms, is the noise. When both come together at the right moment, the climate can flip from one state to another. This explains something else too. If you look at the history of ice ages, you notice they aren't exactly the same every time. Sometimes the swings are bigger, sometimes a little smaller. Sometimes the planet warms up a little early, sometimes later. The timing is regular, but not perfect. That fits with the stochastic resonance idea. The system is pushed by a regular force, but it is also subject to random events. Let's talk about the numbers for a second. The changes in Earth's orbit, those Milankovitch cycles, change sunlight by only about 1% or 2%. Not much. But ice ages are huge events. Ice sheets thousands of feet thick. Sea level changes of over 400 feet. That is a massive swing. All from a tiny push and some noise. One of the clearest signs of this comes from ice cores in Antarctica and Greenland. When scientists drill deep into the ice, they see layers going back hundreds of thousands of years. In those layers, they find signs of sudden jumps, abrupt changes in temperature, greenhouse gases, even dust. These jumps often align with the timing of orbital cycles, but they aren't always right on schedule. Sometimes a random event seems to help tip the system. A big volcano or a sudden change in the ocean might be enough to push the planet over the edge. Another clue comes from the sea floor. In the mud under the ocean, there are layers that show when ice sheets grew and shrank. These layers match up with the ice cores and the timing of orbital changes. But again, the record isn't perfect. There are little wobbles and times when the system seems to skip a beat. That is exactly what you would expect if stochastic resonance is at play. The system is regular but not a perfect metronome. And here is a twist. Before about 1 million years ago, the Ice Age rhythm was different. The planet flipped from cold to warm every 41,000 years, not 100,000. This matches a different orbital change, the tilt of Earth's axis, which changes how sunlight hits the poles. But then about 1 million years ago, the rhythm shifted to this longer 100,000-year beat. Scientists call this the mid-Pleistocene transition. No one knows exactly why the system changed gears, but it suggests that the way noise and regular pushes interact might change over time. Maybe ice sheets got bigger and more stable. Maybe the ocean changed the way it stored heat and carbon. The rules of the game shifted. Let's get back to what this all means. The story of ice ages isn't just about one thing. It isn't just orbit or just ocean or just CO2. It is about how small, steady changes and random, unpredictable events can team up to do something much bigger than either could do alone. Think of it like a lock and a key. The orbit is the key turning slowly and steadily. The noise is like your hand jiggling the lock as you turn. Sometimes the key and the jiggle align, and the lock opens. The system flips from one state to another. This idea helps explain not just ice ages. It is a reminder that nature is full of surprises. Sometimes a little randomness is exactly what you need to reveal a hidden pattern. The world isn't always smooth and predictable. Sometimes chaos helps make order. There is something oddly comforting in that. The Earth isn't just a giant clock counting down the years. It is a living, breathing system. It reacts to small nudges and big shocks. It does the unexpected sometimes. But even in the middle of all that chaos, there is a rhythm, a pattern you can see if you stand back far enough. So when you hear that ice ages come and go every 100,000 years, remember this: it isn't just the math of orbits. It isn't just slow ice buildup or sudden carbon release. It is a dance between order and chaos, between the push and the random noise. Together they make the climate swing. And this idea, stochastic resonance, is one of the best theories we have for why the timing of ice ages is so regular. It isn't a perfect answer. There are still mysteries. We don't know exactly what all the sources of noise are. We are still learning how ocean, atmosphere, and ice all work together. But it is a good start. It shows that even the biggest swings in Earth's history can come from small beginnings. A little push here, a random nudge there, and the whole world can change. Sometimes that is all it takes. And here is the big picture. Earth's climate system is balanced on a knife edge. It takes just a little push and maybe a little luck to tip it from one state to another. The regular beats of the orbit give us the rhythm. The noise gives us the surprise. So next time you wonder why the planet freezes every 100,000 years, think about swings and locks and noisy systems. It isn't just the strength of the push. It is when the push and the noise come together, that is when the magic happens. But there is still more to the puzzle. All of these things, orbits, noise, ice, ocean, work together in ways we are only beginning to understand. And if you look back far enough, you see something even stranger. About 1 million years ago, everything changed. The rhythm of ice ages slowed down. Something in the system shifted, and scientists are still trying to figure out what happened and why. So what does all this mean for our future? Let's zoom in to the time we are living in now, the current interglacial period. It is the warm stretch between ice ages. Scientists call it the Holocene. It started about 11,700 years ago. That might sound like a long time, but on the scale of Earth's history, it is just a blink of an eye. Think about it. If the entire history of the planet were 1 year, the Holocene would be the last few seconds before midnight on December 31st. So what is special about the Holocene? Well, for one, it is the time when humans built everything. Cities, farms, writing, all of it. Before this time, life was wild and cold. Now the land is mostly green, ice sheets are small, and the climate has been, at least until recently, pretty stable. But how do we know just how unusual the Holocene is? And what makes this warm period different from all the other warm periods in the past? Let's peel back the layers of evidence and see what the planet has to say. First, let's start with the ice. Although glaciers melted back at the end of the last ice age, a few giant ice sheets still remain, mostly in Greenland and Antarctica. But during the last glacial maximum, which was only about 20,000 years ago, things looked completely different. Massive sheets of ice covered Canada, northern Europe, and parts of Asia. If you had lived then, you would have seen walls of ice higher than skyscrapers stretching for thousands of miles. As the world slowly warmed, the ice sheets shrank. Ocean levels began to rise, swallowing land bridges that once connected continents. That is why you can't walk from Siberia to Alaska now, but people could during the Ice Age. Evidence for this is everywhere. You can find old shorelines on land where the sea used to reach. In some places like Scandinavia, the land is still slowly rising, bouncing back from the weight of the old ice. Now look at the mud at the bottom of the sea. Remember those tiny fossils, the forams. When you look at layers from the Holocene, you see a big change. The shells show the ocean warmed up fast. The amount of carbon dioxide in the air jumped, and the chemistry of the water shifted. These shifts all align with the melting of the ice and the start of the new warmer era. But here is the cool thing. The Holocene isn't the only warm period in the last 1 million years. There have been at least 8 or 9 other interglacials since that big shift to 100,000-year cycles. Some were longer, some shorter, some warmer, some cooler, but they all shared one thing. They were short islands of warmth in a long sea of cold. Scientists figure this out by looking at ice cores from Antarctica and Greenland. Each layer of ice is a slice of ancient climate. By measuring bubbles of old air and dust and chemistry, they can build a record stretching back almost 1,000,000 years. The pattern is clear. Every 100,000 years or so, the world warms up for a brief time, usually about 10,000 to 15,000 years. Then, almost like clockwork, the ice comes back. Let's talk numbers for a minute. During the coldest parts of the last ice age, average global temperatures were about 9 degrees Fahrenheit colder than today. That might not sound like much, but it is the difference between a Canada covered in ice and the forests we see now. Sea levels were about 400 feet lower. You could have walked from England to France. Mammoths and woolly rhinos roamed the plains. Then about 20,000 years ago, the world started to warm. By 14,000 years ago, ice sheets were melting fast. Huge floods poured into the oceans. Sometimes lakes trapped by ice would burst, releasing even more water all at once. The landscape changed rapidly. Forests and grasslands spread north as the ice retreated. Animals followed. People did too. The start of the Holocene wasn't smooth. There were wild swings like the Younger Dryas, a sharp snap of cold that lasted about 1,200 years. Evidence for this comes from pollen in ancient lake mud and tiny crystals in Greenland ice. Suddenly, near the end of the Ice Age, temperatures plunged back down. Then just as fast the cold ended, and the world warmed again. Once the Holocene truly began, things settled down. For the last 11,100 years, the climate has been unusually stable. Temperatures went up and down a bit, but not much. The pattern is almost flat compared to the wild swings before. Scientists sometimes call this time the long summer. Why does this matter? Because stability gave humans a chance to build. Before the Holocene, humans lived by hunting and gathering. They moved when the weather changed, following animals and wild plants. But when the climate stabilized, people could start farming. They planted crops, raised animals, and stayed in one place. Villages grew into towns, towns into cities. Civilizations rose all over the world. So how do we know the Holocene was actually stable? And not just in one place, but everywhere? The answer comes from dozens of clues. There are tree rings that show how wet or dry each year was. Pollen in lake mud that tells us what kinds of plants grew. Cave formations like stalactites and stalagmites that grow faster or slower depending on rain and temperature. All these records agree. The Holocene has been a calm time, but it hasn't been perfectly flat. There were smaller wiggles in the climate. For example, about 8,200 years ago, there was a sudden cold snap that lasted a century or two. Scientists think it was caused by a giant lake in North America draining into the Atlantic, disrupting ocean currents. There was also the so-called 4.2 kiloyear event about 4,200 years ago. This was a drier, cooler period that hit ancient Egypt and Mesopotamia hard. Some kingdoms collapsed, others barely survived. Then there was the medieval warm period about 1,000 years ago when parts of Europe became warmer. Vikings sailed to Greenland and even North America. Later came the Little Ice Age from about 1300 to 1850. Winters in Europe were colder. Rivers froze and crops sometimes failed. But even these changes were small compared to the giant swings of the Ice Age. Let's pause for a second and think about what the evidence actually shows. In Greenland ice cores, layers from the Holocene are thicker and more even. There are fewer big dust spikes. The amount of carbon dioxide in the air stays stable in a narrow range, about 260 to 280 parts per million, until very recently. Tree rings from around the world show the same thing. Some years are better than others, but the pattern is gentle. No deep freezes, no wild heat spikes, This climate calm is a rare thing in Earth's story. If you look at the last million years, most of the time is cold, dry, and difficult. Warm periods like the Holocene are short and precious. They are like breathing spaces between long icy winters. Now let's talk about animals and plants. During the Holocene, forests grew back where ice had scraped the land bare. Animals like deer, wolves, and bison spread into new areas. Some huge creatures from the Ice Age, like mammoths and giant sloths, didn't make it. They disappeared as the climate warmed and humans spread out. But many species found new homes. There is a story in the mud at the bottom of lakes and oceans too. Layers from the Holocene are full of pollen from trees and grasses. You can see forests marching north over thousands of years. In some places, ancient seeds and leaves are still preserved. They show how fast the world changed as the ice retreated. In Europe, forests came back first in the south, then spread north as it warmed. In North America, the same thing happened. Birch and pine gave way to oak and maple. Animals followed the trees. People did too. The story repeats in Asia, Africa, and South America. Evidence is everywhere. In cave paintings, in ancient campsites, in piles of shells left by people eating near the sea. Life changed along with the land. But the Holocene isn't just a story of nature. It is the stage for human history. The first farms appeared in the Middle East about 10,000 years ago. Wheat, barley, and lentils were planted. Sheep and goats were domesticated. Soon rice farming started in China. Corn, beans, and squash were grown in the Americas. All of this happened during the Holocene. Without a stable climate, it probably wouldn't have been possible. Let's look at the numbers again. Before farming, the world population was tiny, maybe a few million people scattered in small bands. By the time the first cities rose about 5,000 years ago, there were tens of millions. Today there are over 8 billion. That is a huge change, and it all happened in this warm window. What about the world's ice and so? Greenland still holds a big ice sheet, but it is much smaller than it was during the Ice Age. Antarctica is even bigger, but most of it is far from humans. The last bits of ice in North America and Europe melted away about 8,000 to 6,000 years ago. The evidence shows this clearly. Old shorelines, buried soils, and ancient pollen tell the tale. As ice melted, sea levels rose fast. In some places, the ocean swallowed land where people once lived. There are underwater ruins even off the coasts of India and the Mediterranean. People had to move as the seas came in. Let's not forget climate surprises. Even in the Holocene there were droughts and floods. The drying of North Africa about 5,000 years ago turned green grasslands into the Sahara Desert. Evidence for this comes from ancient lake beds, buried dunes, and even cave art showing animals that don't live there anymore. Other places got wetter for a while. The monsoon in Asia shifted, flooding some areas while drying out others. These changes show up in river mud, lake layers, and even in the rise and fall of ancient kingdoms. But again, none of these shifts match the wild swings of the Ice Age. Now, what about carbon dioxide and greenhouse gases? For most of the Holocene, carbon dioxide stayed in a narrow band. As we said before, that is what you see in the ice cores. Only in the last 2 centuries has it shot up, mostly due to burning coal, oil, and gas. This is a new thing, and scientists are watching closely to see what happens next. But for now, let's stay in the past. The calm of the Holocene wasn't guaranteed. In a way, it was just good luck. The planet's orbit, tilt, and wobbles aligned to give us a break between ice ages. If you look at the timing, we are actually due for at least another cool period, based on the old pattern. But something is different now. The amount of greenhouse gases in the air is higher than at any time in the last 800,000 years. The Earth is warming fast, That doesn't usually happen near the end of an interglacial. Scientists are trying to figure out exactly what that means. For most of the Holocene, life was shaped by gentle changes. Rivers shifted, forests grew and shrank, humans learned to farm, and animals found new places to live. The proof of all this comes from rocks, mud, ice, pollen, tree rings, and even human bones and old tools. You can see the marks of ancient farming in the soil. Old fields in England, rice paddies in China, terraces in Peru. These are all signs of people using the calm weather to build something lasting. So what is the takeaway from all this? The Holocene is rare. It is a gift of the planet's strange heartbeat, a pause between long freezing winters. It has been stable but not perfectly calm. There have been bumps and shivers, but compared to the wild rides before, it has been paradise. All the evidence aligns. Ice cores, mud, pollen, tree rings, lake layers, ancient shorelines, they all tell the same story. A long, warm window just right for humans to settle down and build. Will it last? That is the big question. If the pattern of the last million years holds, another ice age should come someday. But with the new spike in greenhouse gases, the future is open. The story of the Holocene is really our story. We are here because the Earth got lucky. The evidence is all around. If you know where to look, in the quiet layers of mud, the frozen bubbles of air, the rings of old trees, the seeds of ancient farms, it is strange to realize how tied we are to the rhythm of a planet. One long summer, and here we are. Cities, science, art, everything, a calm between the storms. So when you look at a map or watch the seasons change, remember that this isn't normal for Earth. It is special, and it won't last forever. Let's take a step back for a minute and look at the truly big picture, not just a few thousand years or even a few ice ages. Let's talk about deep time, the kind of span that makes your head spin. This is what the world looks like when you zoom way out, far beyond human history, beyond even the first humans. We are talking hundreds of thousands, even millions of years. It is hard to imagine, but understanding deep time is the only way to see why the planet freezes and thaws over and over again. So what does deep time look like? Imagine a timeline stretching across your entire neighborhood. The part with humans, cities, and farms would be a tiny scratch at one end. Most of that timeline would be empty of us, filled with things we can barely imagine. Strange animals, shifting continents, and endless cycles of ice and fire. Here is the thing about Earth. It is always changing, but not in a smooth, gentle way. It swings between extremes. For most of its history, the planet was either much hotter than it is now, or much colder. Yet the last few million years have been special. That is when the Ice Age cycle really began. Sometimes the world is covered in ice. Sometimes it is warm and green. But these turns don't happen at random. They follow a pattern. Scientists call this the glacial cycle. It isn't just one long ice age. Instead, ice comes and goes in waves. The cold spells last about 90,000 years. Then there is a short warm break, an interglacial period like the Holocene we live in now. Then the ice returns. It is like taking a breath in and out, but each breath takes 100,000 years. But why? What sets the rhythm? To answer that, we have to talk about things even bigger than the Earth itself. We have to look at the sky. Here is where it gets really interesting. The main driver behind these giant swings isn't volcanoes or meteor impacts. It is the way the planet moves through space. Earth doesn't just spin and circle the sun in a perfect loop. Its path is a bit messy. The orbit wobbles, the tilt of the axis shifts. The shape of the path around the sun changes. These slow, steady changes are called Milankovitch cycles, named after Milutin Milankovic, the Serbian scientist who figured them out about 100 years ago. Let's break it down. There are three main things going on. First, there is the shape of Earth's orbit. Sometimes it is more like a circle, sometimes more like an oval. This cycle takes about 100,000 years. When the orbit is more oval, Earth swings closer and farther from the Sun during the year. This changes how much sunlight reaches different parts of the planet. Second, there is the tilt of Earth's axis. Right now, the planet is tilted about 23.5 degrees, but that angle changes over time, rocking between about 22 and 24.5 degrees. This tilt cycle takes about 41,000 years. When the tilt is bigger, summers are hotter and winters are colder, especially near the poles. When the tilt is smaller, you get milder seasons. Third, there is a wobble called precession. Imagine a spinning top tracing a circle as it leans over. Earth does the same thing, but much slower. It takes about 26,000 years for this wobble to complete a full cycle. It changes the timing of the seasons, making northern summers happen at different points in the orbit. Now, these three cycles don't line up perfectly. Sometimes they add up to make summers in the north really strong. Sometimes they cancel each other out, making weak, cool summers. And here is the key for ice ages. Those northern summers. Why the north? Most of the planet's big land masses are in the northern hemisphere. That is where giant ice sheets form during cold times. If summers there are weak, snow from winter doesn't melt. Year after year, ice builds up. If summers are strong, ice melts back. To sum it up, about every 100,000 years the planet's orbit tilt and wobble align just right or just wrong, depending on how you like your weather. Summers in the north get weak. Ice starts to form. Over thousands of years, glaciers grow and spread. Sea levels drop as water gets locked in ice. Then, when the cycles shift again and summers get strong, the ice melts, oceans rise, the world warms up, plants and animals move north, humans follow. But here is a weird thing. The timing of these cycles matches the evidence almost too well. When scientists drill into ancient ice or look at layers on the ocean floor, they see the same pattern over and over. About 90,000 years of cold, about 10,000 years of warmth, then the cold returns. The match with Milankovitch cycles is close, but not perfect. Some ice ages started a little early or late. Sometimes the planet stayed cold even when the cycle said it should warm up. This led to a big puzzle. If the cycles are always working, why don't ice ages start and end at the exact same time every time? And what about greenhouse gases like carbon dioxide and methane? These change during ice age cycles too. When the world warms, carbon dioxide goes up. When it cools, carbon dioxide goes down. But which comes first, the warming or the rising carbon dioxide? It is a classic chicken and egg problem. Here is what most scientists think happens. The cycles in Earth's orbit and tilt set the stage. They push the climate in one direction or the other. But the planet's climate is like a giant complex machine. If you push it a little, it can swing a lot. When the cycles make northern summers weak, ice builds up. As ice grows, it reflects more sunlight. That cools things down even more. More ice forms. It is a feedback loop. At the same time, oceans and plants start to pull carbon dioxide out of the air. As things get colder, lower carbon dioxide cools the planet further. So a small push from the cycles turns into a huge temperature shift. When the cycles turn and summers get strong, ice melts, carbon dioxide rises back up, and the planet warms fast. That is why the change from cold to warm and back can be so sudden. Sometimes in just a few thousand years the whole world turns from icy to green, like a giant switch. But here is the twist. For most of the last 2 million years, the Ice Age cycle followed a 41,000-year rhythm. Then about 1 million years ago it slowed down. The cycle stretched to 100,000 years. No one is exactly sure why. The best guess is that ice sheets eventually got big enough to change the rules. Once glaciers reached a certain size, it took a bigger push to melt them, so the planet started following the longer cycle. This shift is still a mystery. Scientists call it the mid-Pleistocene transition. Before it, ice ages came and went faster. After it, cold spells lasted much longer. Warm breaks like the Holocene became shorter and rarer. Think about that. For the last million years, the world has been frozen most of the time. Warm periods like ours are the exception, not the rule. If you jumped randomly through time, you would likely land in a cold, dry world, not a green one. Let's look at some numbers. Over the past 800,000 years, there have been about 8 or 9 full ice age cycles. Each one starts with a slow slide into cold. Ice sheets build up, sea levels drop, deserts spread, then a sharp jump to warmth. The pattern is clear in data from ice cores and ocean mud, but there are small differences in every cycle. Some warm spells last longer, some ice ages are colder. Why do these cycles matter for life on Earth? Because they shape everything: where animals live, what plants can grow, where the sea covers land, even how humans move and build. During the last ice age, giant mammals like mammoths, mastodons, and saber-toothed cats roamed the cold plains. When the ice melted, forests returned, and those big animals faded away, replaced by new species. The Ice Age cycles also created land bridges, like the one between Asia and North America. When sea levels dropped, people and animals could walk from one continent to another. When the ice melted, the bridges vanished, and the world map changed again. But deep time isn't just about ice ages. If you zoom out even further, you see even bigger swings. There were times when the entire planet was covered in ice, what some scientists call snowball Earth. At other times, like the age of dinosaurs, the world was much hotter than today. No ice at the poles, thick forests grew near the Arctic Circle, sea levels were hundreds of feet higher. The Ice Age cycles are just the latest chapter in a long, wild story. They started probably a few million years ago because of slow changes in the way continents are arranged. As land moved around, ocean currents shifted, mountains rose, changing wind and rain. Antarctica drifted over the South Pole and froze. All these changes made the planet more sensitive to the cycles from space. So when you hear people talk about normal climate, remember there is no normal. The planet is always in motion. Deep time shows us that change is the only constant. Sometimes change is slow, sometimes it is fast, but it never stops. Think of the evidence. It is all over the world. In Greenland and Antarctica, ice cores show the swings from cold to warm. In deep sea mud, shells of tiny creatures record changes in temperature and chemistry. In ancient lake beds, you can see layers marking wet times and dry times, cold snaps and warm spells. Even rocks under your feet hold clues, fossils of plants and animals that lived in totally different climates. Here is a simple example. In Europe, scientists found pollen from trees that only grow in warm, wet climates right in the middle of layers from an ice age. That means the climate flipped back and forth, sometimes quickly. In North America, giant rocks called glacial erratics sit far from mountains. They were carried by ice sheets, dropped when the ice melted. The ocean floor tells another story. Layers of mud pile up on top of each other. Each one holds tiny fossils showing what temperature and chemistry were like. Scientists can use these to make a record going back millions of years. The pattern matches what we see in the ice cold, then warm, then cold again. There is another clue in ancient coral reefs. Some reefs are high and dry now, far above sea level. That means the sea was higher in the past. Other reefs are drowned deep underwater. That means sea level was lower when they grew. All these pieces fit together to show the same cycles. Now, let's talk about feedbacks. These are ways the climate system can speed up or slow down changes. Ice is a big one. When more land is covered in snow and ice, more sunlight bounces back into space. This cools the planet, so even more ice forms. When ice melts, the opposite happens. Darker land and water absorb more heat, making things warmer. Greenhouse gases are another feedback. When the Earth is cold, oceans absorb more carbon dioxide. When it warms, oceans release that gas back into the air. Plants grow faster in warm times, pulling in carbon dioxide. Big changes in forests and grasslands can shift this balance. These feedbacks help explain why the swings between ice ages and warm periods are so sharp. But not all feedbacks are positive. Sometimes things can slow down changes. For example, as ice sheets grow, they get so heavy they push down the land. This can change how rivers flow and where rain falls. Those shifts might make it harder for ice to keep growing in some places. And then there is randomness, things that don't follow any pattern. Big volcano eruptions can cool the planet for a few years. An asteroid impact can shake things up for decades. But these are rare. Most of the time, the slow, steady push of the cycles is what matters. Some people wonder if life itself can change the climate. And it can. Plants, especially forests and plankton in the ocean, help control the amount of carbon dioxide in the air. When vast forests grow, they pull down carbon. When forests die or burn, that carbon goes back into the sky. Over millions of years, this helps set the planet's thermostat. So what does all this mean for us? It means this moment is a lucky break. For most of deep time, things weren't this easy. The Earth was either too cold or too hot for humans to thrive. Our entire span of history, from cave paintings to space travel, fits inside just one warm burst in a long, icy story. And here is something else. The cycles don't care about us. They will keep rolling whether humans are here or not. We just happen to live in a rare window, when the world is friendly, the weather is mild, and life can spread and build. If you ever feel small, remember, every breath you take, every city, every poem is balanced on the edge of these giant cycles. We are riding the wave of deep time. The ice will come back one day. Or maybe now that humans are changing the atmosphere, the pattern will break. Either way, deep time reminds us that nothing stays the same. What feels normal is really just a pause in a much bigger story. And now, as you drift off to sleep, so what can we really take away from all this? Why does it matter that the Earth freezes and thaws every 100,000 years? Why do we spend so much time talking about ice cycles and deep time? Let's start with something simple. These cycles aren't just background noise. They shaped every part of the world we know. If you look at a map, the mountains, rivers and lakes, many of them are leftovers from the last ice age. The great flat plains of North America and Europe were smoothed by glaciers. The Great Lakes were carved by ice and then filled with meltwater. If you live in the north, even the dirt in your backyard was scraped up and left behind by a moving wall of ice. It goes even further. The places humans live today, the routes we took, even the food we grow, it all traces back to these ancient rhythms. Crops like wheat and barley started after the last ice melted. The forests and grasslands you see are the result of thousands of years of slow warming. Even the animals that survived, from deer to rabbits to songbirds, were the ones that could handle these wild swings. But here is where it gets interesting. If you zoom out, you start to see how fragile this moment is. Human civilization, cities, writing, farming, is all a brand new experiment. Modern humans have been around for only about 300,000 years, but for most of that time, life was hard. The world was cold, dry, and dangerous. People moved with the seasons, followed herds, and scrambled to survive. Sometimes whole groups were lost when the ice pushed too far. We got lucky. The last 10,000 years have been unusually warm and stable. That is when people learned to farm. They built villages, then towns, then cities. Rivers stayed in their banks. Weather was predictable enough for crops to grow. This short window, just a blip on the timeline, gave us the chance to build everything we know. But the ice is never far away. The evidence is everywhere. In Europe, you can find rocks called erratics carried hundreds of miles by glaciers. In Africa, old riverbeds show where water once flowed in wetter times. In South America, fossils of giant sloths are found in what are now dry grasslands. All these signs point to a world that is always changing. Think about humans for a minute. Imagine being alive 20,000 years ago near the end of the last ice age. The world would have felt harsh and empty. Giant ice sheets blocked the north. Mammoths and woolly rhinos roamed cold plains. People lived in small bands, huddled around fires, always moving. Food was scarce. Winters could last for years, but those people were tough. They made tools from stone and bone. They learned to sew warm clothes from animal skins. They painted pictures deep inside caves, maybe as a way to make sense of the world, or just to leave a mark. When the ice finally melted, some groups moved north, following the animals and the fresh land. Others stayed south, learning new ways to live as the climate changed. Now look at us. Most people don't worry about the next ice age. We have houses and heaters and supermarkets, but the cycles are still running in the background. The same changes in Earth's orbit and tilt are still happening, slow as ever. If nothing else changed, in tens of thousands of years another ice age would start. But things are different now. For the last 200 years, humans have started changing the atmosphere. We burn coal, oil, and gas. We cut down forests and build cities. All this adds carbon dioxide to the air, a gas that helps trap heat from the sun. This is new, something the planet hasn't seen before, at least not this fast. Scientists are now asking a big question. Will the next ice age come at all, or have we changed the rules? Some studies suggest the extra carbon dioxide we have added could push the next ice age far into the future, maybe tens of thousands, maybe hundreds of thousands of years. No one can say for sure. Think about that for a second. For millions of years, the world turned between cold and warm. But now, because of us, that pattern might be broken. We have become part of the story, not just as passengers, but as drivers. This brings up another point. Earth's climate isn't just about numbers and cycles. It is about life. Every time the world shifts, animals and plants have to move, adapt, or die. When ice comes, forests shrink and grasslands spread. When it melts, trees grow back and new animals appear. These changes can be slow or fast, but they always leave a mark. Sometimes whole groups disappear. The big animals of the Ice Age, mammoth, saber-toothed cats, giant sloths, are all gone now. Some vanished as the world warmed. Others might have met trouble when humans arrived, hunting them or taking over their land. Every cycle leaves winners and losers. Humans are good at adapting. We learned to fish, to farm, to build. We crossed land bridges and sailed seas. But even for us, big changes are hard. When climates shift fast, there is less time to adjust. Crops can fail. Rivers can dry up or flood. New diseases can spread as animals and insects move to new places. It is a reminder that we don't control everything. The planet is huge and complex. Even small pushes, like a shift in sunlight or a change in carbon dioxide, can be enough to tip the balance. Sometimes a tiny nudge is all it takes to start a big chain reaction. Here is something humbling. Fossils show that life has survived much worse. There were times when almost everything died. Mass extinctions that wiped out dinosaurs or snowball Earth events where ice might have covered nearly the whole planet. Somehow life bounced back. New forms appeared. The world kept turning. But each time, the survivors had to start over. The rules changed. What worked before didn't always work again. A pattern that repeats but is never exactly the same. So where does that leave us? We live in a world shaped by chance, cycles and choices. We are here because of a long chain of events. Some of it we understand, some is still a mystery. The ground beneath our feet, the air we breathe, even the weather outside, it is all shaped by forces we can't see. Some people find that scary. Others find it comforting. There is a kind of peace in knowing that change is normal, that nothing lasts forever. The world is always moving. Ice will come and go. Warm times will return. Life will find a way, even if it looks different each time. Another way to think about it. History isn't just about people, kings, or wars. It is also about the land, the sky, and the deep rhythms of nature. If you go back far enough, you see that humans are just one part of a much bigger story. The story of a planet spinning, tilting, and dancing through space, always changing, always surprising. That doesn't mean we are powerless. We still make choices every day. How we live, what we build, how we care for the land and water, it all matters. We can't stop the cycles, but we can learn from them. We can try to be ready when things shift. We can pay attention to the clues the past has left for us. Think about how far we have come, from small bands of people hunting in the cold to cities that glow at night, from simple tools to rockets leaving the planet. All of that happened in the blink of an eye compared to deep time. It is easy to forget how new it all is. Sometimes it helps to slow down and listen, to see the world not just as it is, but as part of a long unfolding story. The wind in the trees, the shape of the hills, the path of a river, they are all echoes of ice and fire, of warm times and cold. Next time you look at a map or walk down a city street, remember that the ground you stand on has changed many times before. Forests grew and vanished. Rivers shifted. Ice came and went. The world you know is just one chapter in a much longer book. So, what is the lesson? Maybe that nothing stays the same forever. Maybe that we are lucky to be here right now, in this rare warm window. Maybe that the story isn't over. Those cycles will keep rolling with us or without us, but for now we get to be part of it. And in the end, that might be the most amazing thing of all. Out of all possible worlds, we are here, living on a planet that freezes and thaws and spins through space, watching the patterns, wondering what comes next, trying to make sense of our place in it all. If nothing else, the Ice Age cycles remind us to stay curious, to look for clues, ask questions, and never take the present moment for granted. The world is full of surprises, both big and small. Every day we walk through the results of ancient changes. Some we notice, most we don't. The next Ice Age might be far away, or maybe it will never come at all thanks to what humans are doing. Either way, the story of Earth is still being written, and for now we keep watching, learning and wondering. So as you drift off to sleep, let your mind wander through deep time. Imagine the glaciers growing and shrinking, the forests spreading, the rivers carving new paths. Picture the changing world, slow and steady, always moving forward. You are part of that story too, a small piece of a planet that never stops. Rest easy, knowing that change is the only constant. The ice will return, or maybe it won't, but the story goes on, and you, for this moment, are right in the middle of it. Good night.